Algebra 2, Lesson 2.1, Relations and Functions. A relation is a set of pairs of input and output values. So here I have two examples of relations. The first one is called a circle mapping. And in the circle mapping, I have the pink circle, which is the input values. And for every input value, there is an output value. So notice how there is an arrow going from -2 to 5. So the input value is -2 and the output value is 5. The same is true for 0. 0 is the input value and it's pointing to -3, which is the output value. And 1 is also pointing to -3. So the input values are the x values and the output values are the y values. So any set of pair of points is called a relation. On the right-hand side, we have some other relations, and the first one, the first point is 4, 6. So this is a set of x, y values, the input being the x and the output being the y. And if we put all of these points together, we call it a relation. Relations can also be done with a table. So the table here is the x is the input and y is the output. So we have -1, 4. So if we were to write that in ordered pair form, we'd have the point -1, 4. We also have the point 1, 5 and the point 3, 6. So that's a relation because we have sets of input and output values, x and y values. And we can also represent this relation with a graph. So if we were to graph the input with its output value, the first one we would start with -1, 4. So we would end up with this point. The second one would be 1, 5. That would be right here. And the last one is 3, 6. And that would be right here. So this is a relation graphed. And a relation can have as many points as we want, as long as it's a set of input and output values. So here's a real-world problem. So when skydivers jump out of an airplane, they experience what's called free fall. The photo shows various heights of a skydiver at different times during the free fall. Ignoring air resistance, how can you represent this relation in 4 different ways? So the 4 different ways are a mapping diagram, listing ordered pairs, making a table, and a graph. So we've got 3 of the 4 right here, and the one that we're missing is the table. So in our diagram with the airplane, we are told that at 0 seconds, the height of this free-falling skydiver is 10,000 feet. And then we have a second picture. After 4 seconds, after this person has left the airplane, they're now at a height of 9,744 feet. All right, so the mapping diagram. So the input values are the number of seconds. So right here at 0 seconds, he's at 10,000 feet. That means that he is still in the airplane. After 4 seconds, he's at 9,744 feet. After 8 seconds, he's at 8,976 feet, and so on. We can take these same ordered pairs, our same mapping diagram, and turn them into ordered pairs. And those ordered pairs then translate into the graph. So this person started out at 10,000 feet, and after every second he fell a little bit, then a little faster, faster, and faster, and eventually he would hit the ground, which is what a skydiver would need to do. But he would, of course, open his parachute. Okay, so now what we need to do is turn this into a table. So in a table, we have the input values and the output values. And the input values are always the x's, and the output values are always the y. So what we're going to do is we're going to look at these ordered pairs. So right above here, the ordered pairs, and we're going to list them in table form. So at time equals 0, the output is 10,000 feet. After 4 seconds, he's at 9,744. After 8 seconds, they are at 8,976 feet. So this person continues to drop in the free fall until he opens his parachute. So we could continue listing the other 2 ordered pairs in our table. All right, so there are a couple components to our input and output values, and they are called the domain and the range. The domain is the set of input values. Okay, so if we were to consider this relation, okay, so that's a relation because there is a set of ordered pairs. The domain would be the input values, and the input values are the x values. Okay, so we would say the domain in this case is 3, 5, and -2. The domain is 3, 5, -2. The range is the set of output values. So those are the y values. So for the range, the y values in this case are 0, 7, and 6. Okay. Normally we list the domain and the range in the order of least to greatest, so I'm going to reorder these. So our domain would be -2, 3, 5, and the range would be 0, 6, 7. The next question is to determine if a relation, the set of all of these pairs, is a function. Now, in a circle mapping, a relation is a function if for every value in the domain, there is exactly one output. So for each domain, there can be one output. Okay, so what we're going to do is we're going to take a look at each value. So let's start here with 6. 6 maps to 6, and it has exactly one output. 4 maps to 3, and it has one output. 3 maps to -1, and it has one output. So far we're so good. But notice with number 2, for the input of 2, it maps to -3, but also 2 maps to +3. Therein lies a problem. So the input value of 2 has 2 outputs, not just one. So we would say this is not a function. Okay. In the second example on the right, think about whether or not this is a function. Does every item in the domain, the x values, have one output? And if you take a look here, -3 maps to -2, 0 maps to 7, and 4 maps to 1. So yes, this is a function. When we look at a graph, we have what's called the vertical line test to determine if something is a function. If a vertical line passes through more than one point on the graph of the relation, then the relation is a function. So let's go ahead and use the vertical line test to determine if these relations are functions. So what we're going to do is we're going to draw through these graphs vertical lines, and if ever the line passes through the function at more than one point at a time, then it's not a function. So let's just take a look at this one right here. Notice how that vertical line goes through 2 points on that circle. That means that this is not a function. B. If you look here, for each and every time that this vertical line goes through only one dot on that function. So this is a function. And then the last example, notice how every time I go through that squiggly line, I only touch the line once every time, so that means it is a function. So part A is not a function, but B and C are both functions. Alright, so now that we know what a function is, we need to talk about notation. So a function rule is an equation that represents the output values in terms of the input values. So I know most of you have seen this f of x notation. F of x just means that we have a function, and the function rule is 3 times x plus 2, or 3 times the input value plus 2. And the input value is what we're going to plug in for x. We can also write a function rule with y, and this is maybe more common. Y is the output, and the x is the input. So if we're evaluating this function for the value of 3, 3 would represent the input. So what we would do is we would take and plug 3 in for the x and then simplify. So using our order of operations, we would multiply first and then add. So f of 3 is 11, which means the input is 3 and the output is 11, written as an ordered pair. Evaluate f of -2. So what we're going to do is this time we're going to plug -2 in for our x. 3 times -2 is -6, plus 2 is -4. So the output value is -4. So our function is -2, -4 as our input and output values. Couple more vocabulary words for you. Independent variable. The independent variable is x. And that's because we get to choose the x value or whatever value we're plugging in. Okay, so our independent variable is x, or our input value. And what we get out depends on x. So the dependent variable is y, and that's our output value. So after we pick an input value, we evaluate that, and then we get an output value back, which is our y. So that's dependent. X is independent, y is dependent. All right, so now we're going to write our own function value. So tickets to a concert are available online for $35 each, plus a handling fee of $2.50. So imagine that we're taking you guys all to Chanhassen, and the cost of a ticket is $35 per student, but then we also get charged $2.50 to get all of our tickets sent to us. So the handling fee of $2.50 is a one-time fee. All right, the total cost is a function of the number of tickets bought. So depending on how many tickets that we buy will determine the output value of our cost. So the independent variable is the number of tickets because we get to choose that. The dependent variable is the cost, the total cost, and that depends on the number of tickets. So the total cost is the dependent variable. All right, so let's write out in words what's happening here. So the total cost is the cost of the ticket times the number of tickets plus the handling fee. So if we were to figure out the total cost, the cost is dependent on the number of tickets. So we're going to write a function. So the total cost of the number of tickets, C is for the total cost, T is for the number of tickets, is the $35 times the number of tickets plus the handling fee. So right here is a function that represents the total cost. So now we're going to use our function to determine how much 4 tickets will cost. So we're going to evaluate the cost for 4 tickets. So we take 35 times 4 plus the $2.50. Go ahead and evaluate that. So 35 times 4 is $140 plus the $2.50 equals $142.50 to purchase 4 tickets. And that concludes lesson 2.1.